We now go on to another phenomenon, the fountain effect. What you see here is a tube which narrows down and then opens into a bulb. A small piece of cotton is stuffed into the constriction between the tube and the bulb. And the bulb has been tightly packed with one of the finest powders available, jeweler's rouge. A second wad of cotton keeps the powder in the bulb. This powder presents extremely fine capillary channels. Their average diameter is a small fraction of 1 micron. This device has been placed in the dewar. The liquid helium is below the lambda point. We submerge the bulb, and then we'll send a beam of light from this lamp to a point near the top. You will see the light beam when the lamp is turned on. It focuses some heat in the form of infrared radiation on the point in question. The temperature will rise above the temperature of the rest of the apparatus. Let us turn it on. Liquid helium flows through the hole in the bottom of the bulb, through the fine powder, and rises above the level of liquid helium outside. The height to which it will go depends on the temperature increase produced by the lamp focused on the bulb. We can very well ask, where does the mechanical energy come from that does the work necessary to pump the liquid above the ambient level? Before we attempt to discuss this question, there are two other facts that should be noted. The first is by now obvious. The upward flow through the bulb must clearly be a superflow. Only the superfluid component of helium-2 could get through. The second fact is more significant. Let me explain it this way. The superfluid flows spontaneously from A to B, from a cooler to a warmer place. Point A is in the cold liquid, but B is being heated with infrared rays. The second law of thermodynamics positively says that heat cannot of itself flow from a point of lower to a point of higher temperature. What does this mean to us here, knowing as we do that the superfluid is flowing from a colder to a warmer spot? Simply this: it carries no heat, no thermal energy. Any internal energy it may still possess is no longer thermally available. To say it precisely, it has zero entropy. We have discovered another remarkable property of helium-2. Its superfluid component not only is friction-free, it also contains no heat. The heat energy contained in helium-2 as a whole resides, all of it, in the normal component. We may, of course, add heat to the superfluid component, as we are doing when it passes the spot heated by the lamp. But in doing so, we are converting it into the normal component. Let me return briefly to a question posed earlier. Mechanical work is done in pumping the liquid above equilibrium level. Where does it come from? I cannot answer this question here in full. Let it suffice to tell you that we are dealing here with a heat engine. The mechanical energy comes from the heat added at the light spot. An amusing demonstration of the same phenomenon again uses a bulb packed with rouge, but this one opens into a capillary. Light is beamed on a spot just below the capillary, and it produces a helium fountain. The phenomenon in this and the previous experiment has become known as the thermomechanical or the fountain effect. Below the lambda point, the superfluid component of liquid helium creeps up along the walls of its container in an extremely thin film. It is known as the Rollin film. This creeping film is a variety of superflow. It is difficult to make the film itself directly visible to you. To show it indirectly, we've put some liquid helium into a glass vessel. It is below the lambda point. There is no porous bottom in this vessel. The film rises along the inside wall and comes down along the outside, collecting in drops at the bottom. The thickness of this creeping film is only a small fraction of 1 micron, and of the order of 2 to 300 angstroms. Its speed, while small just below the lambda point, may reach a value as high as 35 centimeters per second at lower temperatures. Below the lambda point, the superfluid component of liquid helium creeps up along the point. Our next experiment deals with the phenomenon of second sound. We are all familiar with wave motion in elastic materials, be they solids, liquids, or gases. Elastic energy of deformation carried away from a source in the form of waves with a characteristic speed, the speed of sound. Liquid helium is an elastic substance, both above and below the lambda point. Both helium-1 and 2 support sound waves. Now, helium-2, the superfluid phase, also conducts heat in the form of waves. This remarkable property is shared by no other substance. For better or for worse, it has been called second sound. Normal heat conduction is a diffusion process. The rate of flow of heat is proportional to the temperature differences. But in helium-2, it is a wave process. Heat flows through helium-2 with a characteristic speed, the speed of second sound. We shall send small heat pulses into helium-2 from a heater. They will spread away from the heater uniformly, carrying the heat energy with them. The speed of second sound is small, just below the lambda point. In the neighborhood of 1.6 degrees Kelvin, it reaches a value of roughly 20 meters per second, and it is in this range that we will run our demonstration. The experimental procedure is as follows. There are two disks in the liquid helium. They are carbon resistors, with the carbon applied in thin layers on one side of each disk. In this way, good thermal contact is established between the resistor and the liquid helium. The bottom resistor will be used as a heater. Electric current will be sent through it in pulses from this pulse generator by means of the cable you see here. The output of the generator is also connected via a second cable to a dual trace oscilloscope, where it will be recorded on the bottom tray. In other words, it will record the heat pulse as it enters the liquid helium. The pulses have been turned on. They themselves trigger the horizontal sweep of the trace, which records time elapsed. It is calibrated at 1 millisecond per unit on the scale. The pulses are 1 millisecond long. The pulses leave the heater at the bottom in the form of second sound and move up to where they strike the carbon resistor at the top. Being heat pulses, they briefly raise its temperature. The carbon resistor is quite sensitive to changes in temperature. It acts as a thermometer. So, the heat pulse of second sound creates a pulse-like change in the resistance of the disc up here. It isn't hard to convert this resistance pulse into a voltage pulse. What we will do is to maintain a small DC current in the top resistor. It is supplied from a battery in this metal box. The box shields the circuit in order to reduce electronic noise. The voltage pulse is small. In this second box, we have an amplifier. The amplifier output is fed into the oscilloscope, where it will appear on the upper trace. The horizontal time scale on this trace is exactly the same as for the bottom trace. However, the upper trace records voltage changes as they occur in the top resistor, the detector of second sound. The temperature of the liquid is about 1.65 degrees Kelvin. The battery has been turned on. And now the amplifier. Among noise and other distortions in the upper trace, a clear-cut voltage pulse appears, about 4.5 units to the right, 4.5 milliseconds later than the pulse entering the heater. This pulse in the upper trace is also about 1 millisecond long. It is the second sound as it arrives at the upper resistor. The upper trace also shows a strong voltage pulse at the left, simultaneous with the heater pulse. That's due to pickup by electromagnetic waves, with the heater acting as transmitter and the detector as receiver. moving the detector towards the heater. The pulse moves with it to the left. Notice the echoes of second sound which appear on the upper trace while the detector is near the heater. They are caused by multiple reflections between the two resistors. A total of 3 echoes is clearly visible. Moving the detector away from the heater increases the delay. Here we have the resistors at their original distance again. They are 9 centimeters apart. The wave of second sound covers 9 centimeters in 4.5 milliseconds. The speed of second sound is 2 centimeters per millisecond, or 2,000 centimeters per second, or 20 meters per second. Let me return to the discussion of the two-fluid model for liquid helium-2. We find that it gives us an adequate qualitative description for the behavior of helium-2. The superfluid component is frictionless and free of entropy. It is thought to be the part of helium-2 which leaks through the finest pores, which rises up toward the source of heat in the fountain effect, and which creeps up along the walls of the container. The normal component, on the other hand, is viscous and possesses some available heat energy. The normal component is thought to be that part of helium-2 which is dragged along by the rotating cylinder, and which remains behind in the beaker with a porous bottom unless it is first converted to the superfluid component. Now, a model alone is not a theory. It turns out that quantum mechanics has had to be brought to bear on the problem of producing an accurate check between theory and experiment. As is usual, when we attempt to explain a quantum mechanical system by a classical model, this model gets lost, becomes washed out, so to speak. It's there, but then again it isn't. The model is false, but many of its elements survive. That's what has happened to the two-fluid model for liquid helium-2. Helium-2 must now be considered as a quantum mechanical system. It is still true that helium-2 is capable of 2 different types of motion, but we cannot anymore claim that these 2 motions occur on different parts of the liquid or on different groups of helium atoms. Rather, we should look at it all as one liquid system capable of 2 different types of motions simultaneously. The superfluid motion, a perfect fluid flow, reversible in the thermodynamic sense, and the normal motion, a viscous flow, either laminar or turbulent, and irreversible.
好 ，OK 哈，那这个呢哈是有关于，其实这个是一个很有名的影片哈，在介绍所谓的这个超流的这个影片啊。那希望就是说让大家看到，就是说，哎，这个真实的这些量子现象哈，到底是怎么样子啊？好，关于刚刚的那个部分有没有问题？
老师，你可以再解释一次那个那个热机的那个影片吗？
哦，热机的影片是不是 ？OK， 好。
Below the lambda point,
这个
and comes down along its vessel to show it indirectly and through. The second.
好。哎，怎么突然不见了？好，这个哈，这个呢，首先实验的装置清楚了吗？清楚了吗？就是用光加热下面黑黑的东西嘛，黑黑的东西吸光就会发热嘛，对不对？发热，所以下面是热的，但是上面是冷的。好，那好，我细部一步一步的讲哈。那你想想看哈，第一个，我们的氦呢哈，在2.16 K 的时候呢，会进入超流态啊。好，那一开始水，不是水哈，液氦哈，在前面一点点哈。一开始的时候，大家看到这个液面有没有？在这里哈。一开始液面还很低嘛，对不对哈？那我今天在这里头所可以拥有的液体呢，它可以是 这个正常态跟超流态，我还没有开灯之前啊。那开了灯之后，它就加热了。那加热之后会发生什么事情？加热之后呢，我的温度升高了，我的氦呢就变成不超流了。好，那变成不超流之后呢，那你想想看这是毛细管那我们在前一个实验的时候呢，这个能够流进毛细管的必须是超流的氦嘛，对不对？
对。
好，那现在就情况就变成这样。当我这里流进去的氦呢被加热之后本来可以流进去的是超流的氦全部只有超流氦才可以进到里头去那进去之后呢，一加热它就变成不超流的氦了。好，那不超流的氦它就流不出毛细管，对不对？它就被关在里面了。好，可是呢，我现在呢，因为我超流的氦呢继续从毛细管流进去，又加热又变成不超流的氦，对不对？所以它就越来越高，越来越高。有没有看到？它就越来越高。好，那你就看到越来越高的时候，你就觉得很奇怪啦。那明明下面是热的，上面是冷的。那我们现在呢？这里头，而且这个往上走的时候，好像还重力还做功，对不对？好，那这样子就违反了热力学，违反了热力学定律啦。就是说，奇怪，为什么这个就越来越高，对不对？我这样流过去，这样一直流过去，然后这里头越来越高。那这里头光唯一的作用就只是加热啊。所以那怎么办去解释这个问题呢？它已经违反热力学第二定律啦。就是我们没有办法做这样的功啊，就是不做功，然后让它上升，对不对？好，那所以事实上，它的做了功怎么来的呢？其实是这样子。刚刚我们不是讲嘛，进来的时候是超流态的液氦吗？
对。
好，那这个超流态的液氦呢，吸热变成不是进来超流态的液氦呢，它其实是不做功的，因为没有热量，也没有 entropy 它进来不管在上面或者在这边，它只要进来在这边，它都是不做功的。好，那现在呢，它上升的原因是什么？是因为超流的液氦变成不超流了。好，从超流变成不超流的时候，它就吸热了。好，那吸热其实就被卡在这边了，对不对？吸热之后就被卡，它已经变成不超流，它流不出去啦，对不对？所以它的功，请说。
所以它是在上面才吸热，
没有在下面吸热，在下面吸热之后，它就变回不超流了。
但是不超流不是不能上去吗？过不去。
不是，它进来在下面这个地方吸热，它进来的在下面，毛细管在下面这边不是在上面这边毛细管在这个黑球这边了
解。
所以在这边光照了它之后，它就分解成这个不超流的液氦嘛，对不对？OK， 但是下面的超流液氦继续进来，就把它往上推嘛。
了解。
它的能量来源在哪里？能量的来源当然就是从超流变成不超流嘛。对不对？那这样子它就可以把它往上继续推啊。一开始的时候乍看的时候，奇怪，怎么会把它往上推呢？对不对？然后好，没有东西做功啊，我只是照光而已啊。OK， 这样了解吗？它上升的原因是这样子。
所以液态超流它是吃掉能量。
对，不是超流吃掉能量，是超流变成不超流的时候，因为
对，
两个温度差，一个是 2.16K 之下才会变超流嘛。那你照了光，它温度可能升到 4K 好了，或者 10K 好了，它是不是就不超流了？那不超流就不能流回来嘛，它流不回来啦。是这样子的原因。
了解。
OK， 好，还有什么问题吗？
好，感谢。
OK， 好，所以其实这个液氦，超流的液氦，它有很多很多很有趣的现象啦，